I'm Tim. Welcome to my portfolio project presentation, which is on the medical appointment no-show prediction. So without further ado, let's first understand our business problem. The issue nowadays in a medical setting is that the patient is failing to attend the scheduled doctor appointments despite receiving instructions. So in other words, this results in a no-show. But why do we care? Because it's actually a waste of resource, affecting both operational efficiency as well as the quality of the patient care. So we have our client here, a medical ERP solution provider, and they seek for help to tackle this by introducing a machine learning model into their software. This model should be able to predict the patient attendance, helping them to actually optimize the appointment management. And the data set used in this project is essentially a CSV file that contains the appointment records from medical institutions, capturing various attributes related to the patients and their appointments. So, for example, we have the patient demographics data, such as the age and gender, and we have the health conditions data, such as diabetes and hypertension, and we have the appointment-specific details, the schedule and appointment date, and whether the patients will receive a reminder SMS. And most importantly, we have our target, which is a binary indicator representing whether a patient was a no-show or attended their appointment. So together we have 14 features to actually start off with, and let's have a look at our solution approach. So there's like two parts of the solution. So the first part is model development, and then the second part is about system integration. So for the first part, we will create a machine learning model to assess the likelihood of the patient no-shows. And then we'll deploy the model with an API for integration into the client's ERP system. And this actually will allow real-time predictions, as well as streamlining the ERP's existing workflow. So let's have a look at the high-level architecture. So here we started with Snowflake, where we store our CSV data file and perform exploratory data analysis. And now once we have a basic understanding of the data, we'll move on to AWS Stitchmaker for data processing and model training. So once we have the model trained, we'll upload the model artifacts to S3. Later on, we'll retrieve the model artifacts to build our Stitchmaker model. Then we'll deploy the model to a Stitchmaker endpoint. Then later we have the AWS Lambda that will call the endpoint for predictions and also store the predictions back to S3. And as for external application interface, we have AWS API Gateway, which will help to manage API requests and responses. And lastly, we have this Postman to test the deployed model. It will be sending requests to the API Gateway as well as receiving the predictions. Let's look at the first component of the architecture. So we are now in the Snowflake UI. We'll first have to create a database to store our data. So under this data tab, we'll need to go to databases. And we're gonna click add database. And we'll give it a name. And I have it created already. So it's this medical appointment no-show. So under this database, we'll need a schema. I'm gonna click this add schema. I'm gonna give it a name. And I have also created the schema already. So this schema name is appointment schema. And under this schema, then we'll need to create our table. So click create table standard. And here we need to write a query to specify the column name and the column type. And as for my query, so this table I created here is called appointment data. And this is my query that I use to create this table. And I will also include this query into the project asset. And once we have the table created, then we're gonna load our data. So we're just gonna drag and drop our CSV file here. So once we've loaded our data, then we can start looking at our data. Then we can write some query to explore the data. You can quickly run this first line to just have a quick understanding of the data. So as described earlier, so we have the patient demographic data, so such as the gender and the age. And we also have the health conditions data, right? So such as hypertension, diabetes, and alcoholism. And we also have the appointment specific details, right? Such as the schedule day, the appointment day, and also whether or not the SMS was received. And most importantly, our target variable, which is the no-show. And we can see that there's almost like 20% of no-show rate based on a total record of 110,000 medical appointments records. So next up, we'll move on to exploring the data. So to do that, we can set up a few hypotheses. For example, do males tend to miss more appointments than the females? Is there any relationship between the schedule and appointment day difference and the no-show of patients? And we can also know if is the no-show common among the adult patients aged between 18 to 30, or if not, which age group the people would have the higher no-shows. So for the first hypothesis, let's have a look at the query. So by looking at the table, we can see that the males do not tend to miss more appointments than the females. Given that both male and female have similar rate of missing appointments, which is around 20%. And let's have a look at our second hypothesis. At first glance, we can see that there is a total of like 5 appointments with a negative daily difference, and which result in 100% percentage. That actually makes sense because it means that these appointments were scheduled before the scheduled date, not after. That's why it's like showing negative days difference. So this could be due to a data entry error, and we'll fix this later. And then let's have a look at the graph. We can see that for those appointments that the appointment day it's the same as the scheduled day, which is this 0 days difference. We can say that you have the least misappointment rate of 4.6%. And now for time difference between like 1 to 80, and the misappointment rate fluctuates, but generally stays between like the range of 20 to 40%. And for those longer time difference, that's more than 80 days, like on the 83 days difference, we have the 12.5%. In 86 days, we have 16.7. They're pretty low. But if we go a little more days difference, such as day 103, it jumps up to 60% and followed by 75% on day 104. And then if you go even further longer, so let's say 112, and then there's like no missed appointments. And if you go even further, 132 days difference, and we got like 100% disappointments rate. Same as 139, 146, and 151. And so it becomes pretty inconsistent as the time difference increases. So let's move on to our last hypothesis. So you can see the graph here. Now, there's actually not too much difference in terms of the missed appointment rate. But we can also see that for the age group of year 13 to 17, it actually has the highest no-show rate of 26.6, followed by the age group of 18 to 30. They have like about 24.6%. And then the age group of 50 plus, they have the least missed appointment rate of 16.2. And let's have a look at the table. We can see that here for the age group of 13 to 17, although they have like the least appointment schedule, but they do have the highest missed appointment rate. In contrast, for the age group of 50 plus, they actually have the highest number of total appointments scheduled. But in fact, they are the ones who have the lowest missed appointment rate. So that basically wraps up the hypothesis-based EDA. So next we'll move on to the data processing and model training, which will be done in AWS Stitchmaker. We have stored our data and explored our data on Snowflake. So now we can actually retrieve the data in AWS Stitchmaker for data processing and model training. And yeah, so let's go to the Stitchmaker. So here, this is the AWS Stitchmaker interface. So now we will have to create a notebook instance to work with. And I have it created already called the predicting medical appointment no-show. But to create one, we can just quickly click this create notebook instance button. Then we can give the notebook instance a name and then select the notebook instance type based on the need. And then we'll just keep the default IAM row. Then we can just create the notebook instance. So yeah, we can just spin up the notebook instance and just wait for it to get ready. So now that our notebook instance is ready, and we can go to this Jupyter Lab. So here is our Jupyter Lab app environment. And so under this folder icon here, in this side panel, is where we can upload all our project assets. And so earlier in Snowflake, we have the files. For example, the CSV data file, the table creation query, and the EDA query file. They all can be found under this Snowflake assets. So these three files. And then for this project notebook, this notebook actually covers all the details from data processing to model training. So our project notebook is open up. So at the very first, at the very beginning, you can see that the problem statement here, which is the same as the business problem that we have discussed earlier. And then we have the data descriptions that will describe what each column here represents. And then we have the modules importation, which covers all the modules needed for this to run this project. Then next up we have data loading from Snowflake. Before we can actually get to work with the data, so we will first have to retrieve it from Snowflake. So to do that, we'll first have to connect to the database via the Snowflake SQL Alchemy. So this is the first part we do. We create the engine. So we're gonna pass in the parameter like the account identifier, the username, password, the row, the warehouse, database, and schema information. And then we'll write the query to retrieve the table of our data, and then we'll return back as pandas data frame. And at the end, you will also print out whether or not the connection is successful. So optionally, we can also save the data frame to our local disk for it to loop them back to our workspace for analysis. And also at the end of the project, so when we successfully deploy our model, so we'll need a real unseen data to test out our solution. So since we don't have one, I'm just creating one here. And then I just empty the target no-show column, and I just output it as a CSV. The next up, we have a data inspection, and we can have a quick look at the data frame. It should be exactly the same as what we have seen Snowflake earlier. And it should contains like 110,000 of records with 14 features. And we can also see that there's no empty values in each columns. And let's have a look at the data types. So from this table, we can see that there are a few categorical columns: the gender, the neighborhood, and the no-show, which will convert them into numerical so that it can be predicted by machine learning. So we can also see that there are two unique identifier columns: the patient ID and the appointment ID. So we'll drop the patient ID since it doesn't hold any meaningful relationship with our target, but we'll actually set the appointment ID as our index so that each row is unique and we can avoid duplicate records. So next up, we have this hypothesis-based EDA, which is just exactly the same as what we have done in the Snowflake. So I just have it documented down here so that we can actually refer back to our findings. So next up, we'll be performing the data preprocessing. So we'll first drop the patient ID column, then we'll set the appointment ID as our index, then we'll numerically encode the target variable, which is the no-show. Then we can either drop the rows which the appointment day comes before the scheduled day, and lastly we'll drop the rows with -h. And we have another two categorical columns, which are the gender and neighborhood. So we'll numerically encode these two features in the later step. So we'll first begin with dropping the redundant columns. So we'll drop the patient ID. So before dropping, it's like 14 columns in total. After dropping, we have 13. And then we'll reset the appointment ID as our index. Before we do that, we're just gonna quickly make sure that all the appointment ID is actually unique. We don't have duplicate records later. So yes, indeed, the appointment ID is actually the unique identifier. So we just reset the index, and it's essentially the same as dropping one column. So we have one column less, and then we'll numerically encode our target variable. The value for our no-show column, the original value is no and yes, and after encoding we have 0 and 1. Next up, we'll drop the rows for appointment day comes before the scheduled day. So we're just gonna quickly check how many records are there. So there are 5 records with negative days difference. So after dropping these 5 records, and we have 5 rows less. And lastly, we're gonna drop rows with -h. So let's quickly check what's the minimum and maximum h. We have -1 and 115, and just -1 h just doesn't make sense. So we'll quickly check how many -h are there. So there's like 1 record with -h, so we'll drop that row. Now we have 1 row less, and we just verify our minimum and maximum h. We have 0 and 150. After we pre-process the data, we will now apply statistical testing to help understand the impact of the features on our target. So for example, we can perform chi-square tests between the gender and our target variable no-show, and we can also perform chi-square tests between alcoholism column and the target variable no-show. We perform the chi-square test between the gender and target, and as well as alcoholism and our target, because gender and our target are both categorical, same as the alcoholism and our target. So we want to see if the gender actually has impact on our target, as well as if the alcoholism column have impacts on our target. And we can also find out if is sending messages to the patients really helpful, and we can check its significance with the target variable using relevant testing techniques. Here we also use a chi-square test because for the SMS received column and our target variable, they're both also categorical variable. So let's move on to our first chi-square test, which is between the gender and no-show. So we can carry out hypothesis testings. First, we will set up the null hypothesis, which is the gender is independent of whether they will miss an appointment. And for the alternative hypothesis, we can say the gender of the patient is actually not independent of whether they will miss an appointment. We can set a significance level, a threshold of 0.05 for this test. So if the p-value of our test is actually less than the significance level, then we reject the null hypothesis and say that the gender does have an impact on our target variable no-show. So let's actually have a quick look at the impact of our gender on no-show. Here we can see that the female actually schedule more appointments than male, but the no-show rate is actually about the same. Let's verify with our test. So the p-value we obtained from the test is actually 0.172, which is actually more than our preset threshold of 0.05. Therefore, we fail to reject the null hypothesis, and we cannot prove that there's actually a significant relationship between the gender and no-show. So the second chi-square test is actually between the alcoholism and no-show. So the same thing applies. We're gonna set up the null hypothesis and the alternative hypothesis. So for the null hypothesis, we'll say that the alcoholism is actually independent of whether they will miss an appointment. And in contrast, for alternative hypothesis, we'll say the alcoholism is actually not independent of whether they will miss an appointment. So same thing, we'll use a threshold of 0.05. So if the p-value of our test is actually less than our threshold, then we will reject the null hypothesis, saying that the alcoholism does have an impact on the no-show. So we also have a look at the impact of the alcoholism on no-show. Here we can see that there are actually way more non-alcoholic patients than the alcoholic who scheduled for the appointment, but the no-show rate between the two is also about the same. So let's verify with the test. So here we obtain a p-value of 0.96, which is a lot more than our threshold of 0.05. So again, we fail to reject the null hypothesis, and we cannot say that there's actually a significant relationship between the alcoholism column and our no-show. So here it comes to our last chi-square test, which is between the SMS received and the no-show. So for our null hypothesis, we'll say that receiving an SMS is actually independent of whether a patient will miss an appointment. For our alternative hypothesis, we'll say that receiving an SMS is not independent of whether a patient will miss an appointment. So the threshold will use the same 0.05, and for the outcome, we'll expect if the p-value is less than the significance level, then we will reject the null hypothesis, saying that receiving an SMS does have an impact on the no-show. So we also have a look at the impact of our SMS receive on the no-show. So in this graph, we can see that both no SMS reminder received and yes SMS reminder received have about the same total numbers of no-show, but we have actually more patients who did not receive a reminder than received. Let's have a look at our test. So here we obtain a p-value of 0, which is so small that it actually assumes to be 0. So since the p-value is smaller than our preset threshold of 0.05, we are going to reject the null hypothesis, and this time we can say that there is actually a significant relationship between the SMS received and the no-show. So before we move on to feature engineering, so we'll first split the data into the train and test set with stratification to remain the target's class distribution. Let's first have a look at the no-show distribution before splitting. So we have about 20% of no-show rate have discovered earlier in Snowflake, and now we're gonna perform the 80-20 stratified split. So which means that we're gonna serve 80% of the data as our train set and 20% of the data as our test set, with stratification applied to our target column no-show. In this part, we're gonna do the split So the test site we set to 20%, and we apply stratification to our target column no-show. After splitting, we just want to verify that both our training and test set have the same class distribution as before splitting. So we have like 80-20 class distribution, same as the test set, 80-20 class distribution, and before splitting, we're gonna have 80-20 class distribution. And then we'll just verify that the shape of our training set and our test set. Here we can see that we have 80% of the data is being used for the training and 20% of data is being used for the testing, given that we know that we have a total of 110,000 records. So next, we'll move on to the feature engineering, and we'll apply additional data preprocessing if necessary. So here we'll create two features and apply statistical testing to understand if the newly created features have impact on our target. So the first feature will be gender age. It's essentially a combination of feature column gender and the bucket size age column. How do we do that? Is that we will first create a temporary column called the age bucket, then which bucketizes the age into age groups. So like 0 to 12, 13 to 17, 18 to 30, 31 to 50, and 50 plus. Then we will combine the gender column with this age bucket column as together as gender age, and then finally we'll drop the temporary age bucket column. So in this plot, we combine the gender and the age group columns, and then here we drop the age bucket column. Then let's have a look at the impact of our gender age on no-show. Here we're gonna be performing chi-square test because gender age and no-show, they're both categorical. So to set up the hypothesis, we said that there is no significant relationship between the gender age and no-show. And for alternative hypothesis, we said that there is actually a significant relationship between the gender age and no-show. And here we'll use a significance level of 0.05 as our threshold. So for expected outcome, if the p-value obtained is actually less than the significance level, we will reject the null hypothesis, and we'll say that the gender age has an impact on the target column no-show. So let's have a look at our result. So here our p-value here is way smaller than our preset threshold of 0.05. Therefore, we reject the null hypothesis, and we can say that there is actually a significant relationship between gender age and the no-show. The next feature we're gonna be creating is called day steal appointment, which is the day's difference between the scheduled day and appointment day. So we will how are we gonna do it? Is that we're gonna subtract the scheduled day from appointment day. And then we're also gonna be verifying that there's no negative days. And then we're gonna set up the hypothesis testing. So the test we'll be using is called point biserial correlation, because the column day steal appointment is a continuous variable, and our target no-show is actually categorical. So for our null hypothesis, we said that there is no relationship between day steal appointment and the no-show target. As for alternative, we say there is actually a relationship between the day steal appointment and our target no-show column. And we set 0.05 as our significance level. The expected outcome is that if the p-value is less than the significance level, we'll reject the null hypothesis. And let's have a look at our result. So here our p-value is actually very small. We can assume it to be 0, and the p-value of 0 is also smaller than our preset threshold of 0.05. Therefore, we're gonna be rejecting the null hypothesis, and we can say that there's actually a significant relationship between the day steal appointment and the no-show, with a correlation coefficient of 0.18, which is essentially not a strong correlation. Next up, we're gonna be pre-processing our date type columns. So what we're going to be doing here is that we're going to extract the year, month, and day from the datetime columns, scheduled day and appointment day. And then we'll delete the year column with just one unique value. And here we actually drop the appointment days year because it only contains one unique value. Here we actually dropping twice because we're looping through the train set and test set. And then next up is about numeric encode categorical features. So here for the categorical columns, we have the gender, neighborhood, gender age. And let's have a look at our unique values in train set and test set. So for both train set and test set, the gender has 2 unique values, and the gender age has 10 unique values. And as for neighborhood, we have 81 unique values for train set, and we have 78 unique values for test set. After encoding our data, then we'll also make sure that after encoding, we'll get the same unique values, same number of unique values. So let's begin with encoding the gender. So for the gender column, we have male and female, so we'll map male to 1 and female to 0. And then we'll encode the gender age, our newly created column. So here, since the gender age only contains 10 unique values, so we'll be applying the one-hot encoding. Once the gender age has been encoded, we can have a look here. We can see now the gender age is encoded with is one-hot encoded, same as the test set. And then next up, we're gonna be encoding the neighborhood. Since the neighborhood has a high numbers of unique values, so we'll be using a target encoding. After encoding, we have the same unique values as before encoding. So we do a quick check here. So we're also gonna make sure that there's like no missing values. So 0, 0, and the unique values is the same as before encoding 81 and 78. So after all the encoding are done, so we're gonna make sure that there are no categorical columns left. So we just do a quick check. So the number of non-numerical columns in the training set is 0, and same as the test set. Now that we have created the new features and processed the data to the right format for machine learning, and now we will analyze the correlation between the different features to identify if there's a multicollinearity which could impact the performance of some predictive models, such as logistic regressions. So we'll do that by computing the correlation here, and we are actually focusing on identifying very high correlations, such as coefficients more than 0.8 or less than negative 0.8 as our indicators of multicollinearity. So if multicollinearity exists, then we might consider not use one or more of the highly correlated features. So let's have a look at our correlation here. We can see that there's actually no high correlation between any of the pairs, as the highest correlation is about 0.61 and negative 0.61. So we are not dropping any features in this section. Let's move on to tackling class imbalance of our no-show. So we will create 3 sampling data sets with different techniques, such as upsampling, downsampling, and smoked. And then we'll just recall our class distribution of our no-show column. So we have about 80% of majority class 0, and we have about 20% of our minority class 1. Let's first look at our first sampling technique, the upsampling. So the upsampling, basically, it will randomly duplicate the observations from the minority class to balance the data set. And as for downsampling, it's actually the reverse of the upsampling, so it will randomly remove the observations from the majority class to balance the data set. For the last technique, we have smoke. Smoke also upsizes the minority class, but instead of just duplicating the data, Smoke will generate new synthetic samples that are similar to the existing ones. So after creating these three datasets, the class should be balanced in these three datasets respectively. So next up, we'll move on to feature scaling. So here we will apply standard scaler to transform the data into distribution with a mean of 0 and a standard deviation of 1. So here we will we'll fit the scalar on the train set, and then we'll transform on test set, same as for the sampling data set. And then the next up, we'll move on to feature selection. So here we will perform feature selection to identify the most important features for our model. To do that, we will use machine learning models to compute the feature importance. So here we'll use one linear model and one tree-based model. So they are logistic regression and decision tree. So this will actually help us to understand which features are most influential in predicting our target variable no-show. So let's first look at our logistic regression. We will focus on features that have at least 1% importance. So after filtering with 1% importance, we have about 21 features, and before filtering, we have about 25 features. And next, let's look at our decision tree feature importance. We will also focus on the features that have at least 1% importance. And after filtering, we have about 9 important features. And then we'll combine the important features from both the model. In total, we get 22 features. And we'll add the target as well. So altogether, we have 23. And then we'll filter the data set with combined important features. So now that we have our features and data ready, so we can now move on to modeling. First, we'll look at dataset preparation. So here we'll organize the data into input variables and target variable, the X and Y for each dataset. So we do it for the train set, test set, as well as the sampling set. We also have like two separate datasets, the original unskilled datasets and the skilled datasets. So we're gonna use the skilled datasets for the skill sensitive model, such as logistic regression. And for the original unskilled data, so we'll use it for the model that is more robust to the skill, which is the tree-based model. So let's move on to model selection. So here we will train multiple machine learning models. So we're gonna be using logistic regression, decision tree, random forest, and XGBoost with stratified careful cross-validation on our original dataset to identify the one model that actually performs the best based on the metric ROC-AUC. So we will set the class weight to balance for logistic regression, decision tree, and random forest. And as for XGBoost, we will reverse the class ratio. And as a result, XGBoost actually achieves the highest ROC-AUC trained on the original dataset. Now that we know that XGBoost is performing the best, so we will now check if the sampling datasets will actually help the model to perform better. So including the original dataset, we have a total of 4 datasets. So the original, the upsample, downsample, and the smoke dataset. So after training with these datasets, we're putting on the test set to see which dataset is actually performing the best. So here we actually added one more metric, which is the F1 score. By looking at the result, we can see that for the XGBoost trained on the original dataset, it achieves the highest ROC-AUC and also the F1 score. So we continue training the XGBoost model with our original dataset, unsampled and unskilled. So now that we are decided with XGBoost model, because in the earlier step during the feature selection, we decide on selecting the features based on the feature importance of logistic regression and decision tree. Now since that we are gonna be using XGBoost model, so we might as well revisit the feature importance. So here we revisit our feature importance. We will also filter the importance for at least 0.01. So we are now down to 21 features. During the feature selections step, before we actually revisit the feature importance, we actually have 22 features with target with 23. So when we revisit the feature here, we will further reduce the features. Now that we have 21 features. So now that we have like one feature less, so we are able to maintain the model's predictive power even though we reduce one feature. And then we will just save the reduced features for future use. And then we'll move on to fine-tuning our hyperparameter. So here we'll use a package called HyperOp, and the objective is to maximize our main metric, which is the ROC AUC score. And HyperOp actually employs Bayesian optimization to find the best hyperparameters more efficiently compared to a grid search or even random search. Here's actually a general outline of the steps we will follow. So there are like 3 steps. So we will first define the objective function, and this function will take into hyperparameters, train the gradient boosting model, and also return the metric we want. And then the second step, we will define the hyperparameter space. Because XGBoost has a different booster to choose from, so we're gonna stick with the default booster, which is the tree booster. These parameters are the parameters that we're gonna be tuning for our tree booster. At the end, we'll run the optimization. So here's the code for the HyperOp. So first we'll define the objective function, and then we'll define the parameter space, and lastly we'll run the hyperparameter optimization. And we do it for 100 iterations. And then after the hyperparameter tuning is done, so we achieve a best ROC AUC score of 0.744, which is slightly better than before training of 0.734. And then we'll just save the best hyperparameters for future use as well. So now that we have obtained the best hyperparameters, and we also have discovered the best data set to use, the best model to use, that will train our final model. And then we also predict on our test set to see our final evaluation. At the end, we actually improve the ROC AUC score from 0.7309 to 0.7372. And as for F1's score, we improved from 0.4418 to 0.4495. So after we have our best model, so we'll save our final model. And so this final model, we'll use it for building the Stitchmaker model afterwards. So now that we have trained our model, let's now evaluate the model's performance. Let's first have a look at the confusion metrics. So this column here is our true negative, where this column here is our true positive, which represents the number of appointments that were correctly predicted as a no-show and a show respectively. So this column here and this column here, they are our false positive and our false negative. So we can see that the model has a high false positive, indicating that there's actually a high number of actual no-show that were incorrectly predicted as a show. Now let's have a look at how these numbers actually affect on our evaluation metrics. In the classification report here, we can see that due to high number of the false positive, our model has a low precision of 0.32 and for the show class. But it is also able to achieve a higher recall score of 0.74, showing that the effectiveness in identifying the actual show. So this imbalance between the precision and recall actually results in a lower F1 score of 0.45, reflecting that the trade-off between these two metrics. So next we have the ROC AUC curve, which plots the true positive rate against the false positive rate at various threshold settings. So the area under the curve is the measure of the model's overall ability to distinguish between the positive and negative classes. So our model here actually achieved an AUC of 0.73. So the trade-off involved here is that in order to achieve a high recall, which is also equivalent to our true positive rate, so in order to achieve this high recall here, the model will also yield a high false positives. So due to our high false positive count. But ideally, we want a model that has a high recall, but also like a low false positive rate. So if we have a higher ROC AUC score, the model will actually shift more to the left, so something like this. And this would more correspond to an AUC ROC like close to 1. And next, let's have a look at our PR curve, which is the precision recall curve. This curve actually plots the trade-off between the precision and our recall, also at various threshold settings. It's different from ROC curve. This PR curve is actually more sensitive to the positive class performance, so it becomes more useful when we have class imbalance dataset. Especially the case where the positive class is the minority class. So here we have an AUC PR of 0.38, indicating that the model is struggling to achieve a good balance between the precision and recall. So in other words, the model is quite good at identifying most of the actual no-shows, so high recall, but it also incorrectly flags many patients who would have shown up as no-shows. So we have a lower precision. In summary, the areas for improvement is actually the ROC AUC score, even though we have a moderate score of ROC AUC, and this can be further improved. For the F1 score, we have like a 0.45, which suggests that this also could be better improved, especially for the minority class. And similarly, we have a low AUC PR score, indicating that the imbalance between the precision and our recall, and this is also can be improved. And as for classification report, and we saw that there's like the model actually has a high recall for the minority class, but the precision is low. And as for confusion metrics in general, the number of false positive and the false negative, they both could be further reduced for a more balanced model. As for recommendations, I'll go over like the step 2 to step 6, then we'll come back to this step 1. So what we can do is that we can apply more advanced resampling techniques, such as the ADA-SYN or the borderline smoke to balance the classes. We can also apply the ensemble methods, like stacking or boosting, with different base models to improve the performance as well. We also can explore like other algorithms that are more suited for the imbalanced datasets, such as the light GBM and the cat boost. And also we can adjust like the threshold of our model based on the precision and recall trade-off, so that it's more suitable for our specific problem. And then lastly, we can revisit the hyperparameter tuning with a broader or different range of parameters, especially after making changes on feature engineering. Before bringing the project to the next level of complexity, we can actually enhance our feature engineering by creating 2 new features. In a similar studies, by creating these 2 features, the project owner actually is able to significantly enhance the model performance by improving the true positive, true negative, and also reducing the false positive and false negative, improving all evaluation metrics. The 2 new features are the total prior appointments and total missed appointments. So for the total prior appointments, so this feature actually tracks the total number of appointments that a patient has had before the current appointment. And as for the total missed appointment, this feature counts the number of appointments that the patient has missed in the past. By incorporating these 2 historical data points, the model can better understand each patient's appointment attendance patterns, so leading to more accurate predictions. So this basically wraps up the modeling part, and next we'll actually move on to deploying the model. So before we jump straight into deploying the model, so we'll first modularize the code so that some of the code can be utilized during the deployments. So we just first we import the packages, and then we have like 4 modules here. They are like the data loading, pre-processing, feature engineering, and modeling. So basically, for the data loading module, it has all the like data loading functions. For example, we connect the Snowflake database, and then we retrieve the data, and then we reload the data into our local disk. And as for pre-processing, we drop the patient ID, and then we set the patient ID as our index. And then we do the trend test split, and then we encode the categorical columns, and we also apply the scaling. And for feature engineering, we have functions that creates the age gender feature, and then we also have another feature which is the day state appointment, and then we also extract the date time features. And then as for modeling, it contains all the functions for modeling. So let's say for like selecting the important feature based on the feature importance of the model, and then we have hyperparameter tuning, and then we also have like training the model and predicting the model. And then we have this train.py, so which is the file that contains like all the steps needed from start to model training. Another file here we have predict.py, which contains all the steps from processing the data all the way up to predicting the data. If we actually run this train.py, it will give like in the initial evaluation, ROC, AUC, and the F1 score, and then the model will be saved into a path, and then it will output an evaluation report. So if we run this predict.py, so it's actually important here because when we want to test our deploy model with the new unseen data, the data should be like without the target. So let's say we have this simulated set data here. So the data here actually unprocessed. It has this no-show prediction column empty. So and then we can also see there's like the date time format is not processed, and the categorical columns, they are not processed as well. So we need to have this like test data to go through the same exact pre-processing step as how we pre-process our data for training. So, and lastly, we'll append the prediction from the model. So once we receive the predictions from the model, we'll write to a CSV file. An example of the file will be like this. So it has this patient ID, remove and set appointment ID as our index, and then all the columns here are numeric. And then we have our predicted no-show target column. And then after modularizing the code, then we can finally move on to model deployment. So now that we have processed our data and trained our XGBoost model, and we have also modularized the code. From this point onwards, basically like all the steps below here, it's all about model deployment. So let's recall the model deployment step. So we'll first upload the model artifacts to S3, then we'll retrieve all the artifacts and use it to build Stitchmaker model. Then we'll deploy the model to a Stitchmaker endpoint, and then we have AWS Lambda that will invoke the endpoint for predictions, and then we will also store the predictions back to S3, and then we have API gateway that act as like external interface for managing the requests and responses between the Postman and also our backend. And then lastly, we have we're going to use Postman to actually test our deployed API. So we will send an API request, and then we'll receive predictions. So without further ado, let's move on to our Stitchmaker. So our very first step is to actually prepare our model artifacts. So here we actually in this deployment asset folder. So we will upload like all the necessary file and the trained XGBoost model here, and then we'll package them into the model artifacts. So in this this directory deployment asset, we'll have our files to run our model, and then we'll package them as compressed file. And then let's have a look at the content of the directory. So here we have the model, and then we have one hot and encoded train set. So this is just to transform our categorical columns. And then we have this inference.py and also our features. For this inference.py, this is another .py file for handling things such as like loading the model and then processing the incoming data and also generating the prediction. So let's have a look at the inference.py. So there are like three important functions here: the input functions, the model function, as well as the predict function. So basically here in the input function, we just load the data, and then we apply the same pre-processing step and even the feature engineering steps as we did in the code modularization. So basically it's the same code, we just copy from the code modularization. So we just load the model, and then for the predictions, it's actually the same. It's also the same as how we did it in the code modularization. With one thing that we add to this function is that after we get the prediction from our model, and after we append our predictions to our simulated set, then we will actually add a code here to upload the CSV file back to S3. So our step 2 is to actually upload our model artifacts to S3. So the reason why we're uploading the model artifacts to S3 is that we want to ensure that the model artifacts, they are actually available for our AWS services. But first we'll need to actually have the S3 bucket created beforehand. To create one, we can just go to the services, and then we go to this S3. Then it will bring us to this S3 console, and then here we can create a bucket here. So the bucket that I created is called predicting medical appointment no-shows. So what we're doing in this step is that we will first specify the bucket. The prefix is essentially the subdirectory. So in this main folder, we also create a subdirectory. So we'll also specify the region. And if we take a look at the content of our prefix right now, we actually have nothing in there. And then we're going to upload our model artifacts. So this model.tar.gz is actually uploaded. And then we can also do a quick check with the model, and we can see that this model artifact is actually uploaded here in our bucket. And then we'll move on to step 3, which is to create our Stitchmaker model. So here we will actually specify the model data, which is our URL to our model artifacts. So if we go back to our S3 here, we can just copy this URI. This will be actually what we have here. And then we'll create a image container, the framework set to be the SU boost, and our versions to be 1.7-1. And then we also specify the role and our section. And then as for the entry point is actually the starting point for the model inference of operations. So this will pass in our inference.py, and then we'll give the model a name. And then step 4, we'll actually deploy the model to an endpoint. Here we will also give the endpoint a name, and then we'll also specify the computing resource, such as the initial instance count and the instance type. For this serializer and this deserializer, essentially the parameters that are set to handle our input and output data formats. So for the input format, we use this CSV serializer, and our output format is JSON deserializer. So once the model has deployed, then we can go to the Stitchmaker console to have a look. So if we go back to this Stitchmaker console, we can go to under inference, we can go to model. So here we have our model created, so medical appointment no-show model. And then if you go to the endpoints, and we have this our endpoint here, medical appointment no-show model endpoint. So this endpoint is now in service. So we can go back to AWS Stitchmaker. So we will now actually create the lambda function to invoke the endpoint. So to do that, so on the lambda console, we'll go on to the lambda page and choose create function. So on the lambda console, to get here, we can click services and go to the lambda, and it will bring us to this lambda console. And under this function page, we'll create function. So it will bring us to this window here. So in this window, we'll give a function a name. I choose a medical primary no-show lambda, and then I specify the runtime. So here I choose Python 3.8. And then we can actually set the execution rule. We can either create a new one with the basic lambda permission, or we can use an existing one if we actually have one created. And then we'll go on and click this create function button. So next up, we'll actually write our lambda function. So if we have this lambda function created, it will bring us to this page. So under this code tab, under this lambda function.py, we'll paste our lambda function here. So we can just copy the code here and then paste it over here under this lambda function.py. So what this function essentially does is that you will actually receive the event trigger from the API gateway, and then it will invoke the Stitchmaker endpoint and then process the Stitchmaker response. Then finally, it will return a status code of 200, indicating that the request has succeeded. And then it will also include the prediction output in the body. And then we'll click the deploy button to save the changes. And then under this configuration tab, we'll go to this environmental variables. So here we'll actually need to map our endpoint name to the actual endpoint name that we created. So this endpoint name is what we have in the lambda function. So we're gonna map this endpoint name with our actual endpoint name. So after this, then we'll actually go to creating our API. So to do that, let's move on to step 6. So here we will actually create an API, which is essentially a REST API. So this API acts as the front door of our deploy model and external applications to interact with it. So to do that, we'll go on to API Gateway Console and then choose REST API. Then we're gonna choose build, and then will bring us to a new window. So in this new window, we'll select new API, and then we'll give API a name, and then we'll just keep this API endpoint type as original. Just click create API. So after creating API, we'll actually create a method. So the method is essentially the type of the request that we will be sending to the server. And here we'll be sending a post request. So to do that, we'll under this resource page, we'll choose to create method. Same thing, we'll go to services and we go on to API gateway. So under this resources tab, then we'll go create the method. So it will bring us to this new window here. So the method type we'll choose post, and for integration, we want to have it to be integrated with our lambda function. And we'll turn on the lambda proxy integration, and we'll select our lambda functions. So for the lambda function that we created is actually medical appointment no-show lambda. And then we'll just create the method. And after creating method, we'll apply the API in the same resources page. So in the resources page, and then we'll just deploy API, and then we'll bring us to the next window. In the stage selection, we'll select the new stage, and then we'll give the station a name, let's say V1, and then we'll deploy it. So the next step will actually test our API from our local client. In this case, we're actually testing from the Postman. So the first step is to actually we'll actually copy the API URL. So in our created API, so we'll go to the stages page and select the deploy stage, which is the V1, and then we'll copy the info URL. So in this API gateway, so we'll go to stages now, and under this V1 stage name, we'll copy this info URL, and this is the URL that we'll be sending post request to. And then now we are ready to actually prepare our test data. So we'll convert this test data into JSON so that this can be included in the body of our post request. Once our data is prepared, we're ready to test our API with Postman. So the first step is to enter our copied info URL into Postman. So we're going to paste it here. And then we're going to choose the post as a method. And then we'll actually paste our data the JSON string data, and we're going to set our format as JSON as well. And then we will just click send. And then we'll receive the prediction output, which is essentially the 0 and 1s, for example. So in this Postback interface, so this is where we actually paste our info URL from this deploy API v1, and then we'll select this post method, and then we'll click on this body tab, and then we'll paste our JSON string data, and we'll mention that this is a JSON format, and then we'll just click send, and then we'll receive the prediction. And then lastly, we can actually check if the prediction has returned to S3. The reason why our predictions will send back to S3 is that in this inference.py, after making prediction, we said that we wanted to combine the predictions with the features, and then we'll output as a CSV file and with the name of a medical appointment no-show prediction with the timestamp. And then we'll also upload it to the S3 under the bucket predicting medical appointment no-shows and under the subdirectory of predictions. So let's check if the file is actually in the S3 bucket. So under this predicting medical appointment no-shows bucket, and under this prediction subdirectory, and then we have our predictions. So we can just download the data and upload the downloaded data here, and we can open it up. This data actually has been processed, and then it contains only the important features. And finally, we have our predictions from the model as per appointment basis. So that basically wraps up our deployment section. And that's also the end of our project. Thank you for watching.